Hello and welcome back to the Science of Concrete Materials class. This is lecture number 4 and today's topic is the manufacture of Portland cement. Before we get into the manufacturing process, let us get introduced to the cement chemistry, nomenclature, and shorthand notations. Because this is different from what chemists used, and actually chemists may not like this idea, but this is what's used in the cement chemistry and we have to stick with this. Okay, when you see the letter A means alumina, which is the aluminum oxide. C means calcium oxide, CaO. The F means ferric oxide, Fe2O3. H means water, H2O. S means silicon dioxide, SiO2. S bar means sulfate or the sulfur trioxide, SO3. M means MgO, which is magnesium oxide or referred to as periclase. The Na2OE, which is the alkali content, as in terms of Na2O, which is basically the potassium oxide plus 0.658 of the sodium oxide. We'll elaborate on this in later lectures. The cement phases or compounds are as follows. The C3A, which is the tricalcium aluminate, 3 calcium oxide, 1 aluminum oxide. Tetracalcium aluminoferrite, C4AF, 4 calcium oxide, 1 aluminum oxide, 1 ferric oxide. The C2S dicalcium silicate, 2 calcium oxides, 1 silicon dioxide. The C3S tricalcium silicate, 3 calcium oxide, 1 silicon dioxide. Calcium hydroxide, CH, which is, you know what this is. The gypsum, which is the calcium sulfate dihydrate. Calcium sulfate dihydrate, written this form right here, and this is the shorthand notation, C S bar H2. And the calcium silicate hydrate. This is after the cement, reacts with water. We have C-S-H. Okay, you have to get familiar with these notations. Okay, so let's look, at the formal definition of what is Portland cement. According to ASTM C150, Portland cement is a hydraulic cement produced by pulverizing clinker, consisting essentially of hydraulic calcium silicates, usually containing one or more types of calcium sulfate, typically gypsum, as an underground addition. This is the formal definition of Portland cement by ASTM. So how do we need, in order to make cement, we need clinker. How do we make clinker? Basically, the process consists of taking naturally occurring raw material, calcium and silicates bearing material. We crush it, grind it, proportion it based on the required chemistry. If we are using wet process, water is added to the mixture, about 30 to 40% to form a slurry. If not, the dry material is fed to the kiln. Then it is passed through a rotary kiln at a high temperature. This will produce clinker. The clinker is then cooled quickly. After that, it is underground with gypsum. Then we have Portland cement. Okay. This is, a diagram that shows a typical process or typical processes of a kiln. This is general schematic diagram and the actual setup of the kilns might differ dependent, because you might have some of the processes take place outside the kiln. Okay, this is, the typical schematic or generic schematic outline of the conditions and reactions in a typical dry process. And again, when suspension, preheaters are used, dehydration and initial calcining, these processes will take place outside the kiln in the preheater tower. I will show a schematic of that a bit later. But this is generally what happens in a kiln. You see how the kiln, this is basically a long vessel in which certain processes take place. They are dehydration, calcining, clinkering, and cooling. We will define them later. I have to say though about the benefit of a wet process. In the wet process, it helps control the chemistry of the raw material, and also drives off some unwanted impurities such as alkalis. But it is energy, its energy demand is higher. That's why the majority of the clinker produced using the dry process. About 74% of the clinkers produced are using the dry process because it's much cheaper. So let's get into more details. Let's first look at the clinker chemistry, what comes out of the kiln. These are the major phases. The tricalcium silicate, about 50 to 70%. Dicalcium silicates between 15 to 30. Tricalcium aluminate between 5 to 10%. Tetracalcium aluminoferrite 5 to 15%. Of course, we have other, minor phases such as the magnesium oxide, potassium oxide, sodium oxide, and SO3. This is not the SO3 we add through the gypsum, but this is from the clinkering process. The calcium silicate phases, these first two phases, are responsible for the strength. The other phases, the aluminoferrite, the aluminate, and the aluminoferrite, are not of much benefit. Tricalcium aluminate contributes some to early strength, but it poses problems in the sulfate attack issue. The ferrite phase, not much is known about this phase and its contribution to the hydrated Portland cement paste. However, the aluminum and iron are present in the silicate-bearing raw materials, the clays, and one benefit we get from these elements that they work as fluxing agents, meaning they reduce the energy requirements inside the kiln. So they facilitate the formation of calcium silicate phases at a lower temperature than otherwise would be possible without their presence. So these are also intentionally added, if not sufficiently present in the primary raw materials in the form of iron ore and bauxite. And again, they are fluxing agents, and the benefit is they reduce the energy demand inside the kiln. As I said, we have the other minor phases, and impurities, basically from being present in the raw materials or in the fuel. As we sometimes, use waste products, used tires and the likes, to help, again, reduce the cost of the energy in the kiln. These minor phases, I just called them here, these four phases. Okay, so what they do and how they impact the cement and the hydrated cement paste later. The alkali oxides, impact the hydrated products as follows. Alkali hydroxides keep the pH higher, and this help combat corrosion, as we will see. However, they have several disadvantages. They pose a problem with the alkali silica reaction durability issues. Also, at higher concentration, the impact and the nature, they impact the nature of the hydration products. And the issue of the internal sulfate attack. But the internal sulfate attack is beyond the scope of this class, but nonetheless, that's not something I'll mention here just for reference. The higher alkali also, other than the ASR, the alkali silica reaction, they might have an impact with the internal sulfate attack. The SO3 from clinker, not from the added gypsum. Again, sulfate, is needed to control the setting of the hydrated cement paste, as we will see. However, the presence of this compound within the other major phases, like the tricalcium silicate, for example, may prove to be detrimental if present in large quantities. Again, with the issue of the internal sulfate attack, their release later might be problematic. Okay, this is just a quick overview of the cement chemistry and what every element or what every phase does. Okay. In order to form the mentioned phases, the major phases, these here, we need oxides. We need the calcium oxide, we need the silicon dioxide, the aluminum oxide, and the ferric oxide. The ferric oxide, actually, the iron is what gives the gray color to the cement, so just to note. So, where these oxides come from? Raw materials, which is the raw materials basically, they are in two categories. The first one, calcareous material, which provides the lime, which is about 2/3 of the raw meal, and the argillaceous materials, where we get the silicates, about 1/3 of the raw meal. So where we get these materials, what are they? So as an example, the calcareous component, which provides the lime, examples are the limestone, marly limestone, chalk, coral limestone, marble, lime sand, shell deposit, and lime sludge. Examples of the argillaceous component, which where we get these silicon dioxide, the aluminum oxide, and the ferric oxide: clay, shale, calcareous marl, marly clay, tuff, ash, phyllite, slate, and glass. Okay, see these above raw materials, after being selected and quarried, they are then crushed, ground to size, proportioned, weighed, depending on the required chemistry of the clinker, and then they are fed to the kiln. Okay, how do we know how much to get of each material? See these tables on the next slide, this one, I'll talk about them quickly. These are from reference number 2, by the way. These tables show the required raw material composition in order to produce cement with certain phase composition. The phase composition here, the C3S, C2S, C3A, C4AF, they are calculated based on the Bogue method, Bogue equations, and we will talk about these coming up, but just keep that in mind. So we need certain oxide composition of the clinker in order to have this phase composition. And this is the dry raw material composition, what we need to have in order to get this. Okay. This one, the table shows, that in order to get a clinker with certain composition, we need to have, as I said, an ideal material with this composition. This second row right here. Of course, keep in mind, using only one ideal material will limit the options, for selecting the raw materials, which will not be commercially or environmentally viable, because you have to keep looking for this ideal composition for this raw material in order to get clinker. That will not work. So you have to be more creative, selecting more materials that are, consistent within themselves, composition wise, is more viable. So this table here shows, based on two materials, what composition they should have, and gives you more freedom and more options. Okay, this table here shows the options based on using four materials and what composition they will have in order to get this composition of the clinker. And again, having more selections, more materials to choose from will give us more latitude, and it's again more commercially viable and more environmentally viable as well. So okay, let's get back to the process of the clinker or the manufacturing of the cement. We talked about a kiln. So what is a kiln? The kiln basically is a huge inclined, about 1 to 4% over the horizontal rotating furnace, steel furnace lined with refractory bricks. As the raw material of limestone, clay, shale tumble toward a flame of about 1600 Celsius. This is the flame of the temperature of the flame, not the melt inside the kiln. A chemical reaction transforms them into the material we know as clinker. So as a formal definition, the kiln is a continuous stream process vessel in which feed and fuel are held in a dynamic balance. The kiln diameter and length vary depending on the type of the process. What process kilns could be up to 8 meters in diameter, 230 meters long. The typical dimensions of modern kilns about 50 to 100 meters long and about 3 to 10 meters in diameter. The manufacturing process consists of 5 distinct steps: drying, preheating, calcining, clinkering, and cooling. Clinkering here we have to distinguish, from sintering, where no melting occurs, or fusion, where total melting occurs. The kiln is about 1/4 of the charge is liquid. So these, just the terminology you need to be familiar with. This is again the diagram, I showed earlier. This is, shows a schematic of a conventional dry process where, when preheaters and when preheaters are used, dehydration and initial calcining take place outside the kiln in the preheater tower. Again, this is to save energy. Okay? So the kiln setup really has been modified over time. One major reason is to conserve energy. As we said, the cement manufacturing process, energy demand is extremely high. And as I mentioned probably previously in a previous lecture, one of our objectives as an industry is to make the concrete industry more sustainable and less expensive. So we can do that by reducing the cost of energy. So remember, the concrete industry uses about 6% of the world energy. But we do need the concrete because it is a great construction material and we have to have it. So we have to innovate and use innovative ways to reduce the energy demand and make it less expensive. One way we can do that is recycling the heat from the kiln and use it to preheat the raw material and possibly pre-calcine the material. And again, calcination is the decomposition of calcium carbonate. This will reduce the time the raw materials spend in the kiln, thus reducing energy. Just to give you an order of magnitude or a feel of the energy consumption, a typical wet kiln uses about 5,700 kilojoules per kilogram of cement. This is, the dry process kiln uses maybe half of that roughly. That's why, switch to dry process and the use of preheaters and pre-calciner came to be because of the savings it offer and the energy consumption. This is here a schematic of a kiln using the preheater, pre-calciner towers, and again in order to save energy. As you can see, this is the kiln basically right here, and these are the processes. So drying takes place outside the kiln, preheating right here, that's where the feed comes from. Calcining again takes place here, and then this is the sintering process, sintering and clinkering process right here, and of course cooling. You see how the energy demand is split. About 60% of the fuel is split, for this process, and 40% here. So, and again, this preheater, pre-calciner kiln evidently was invented to save energy, as I said. This is here basically a photo of a modern kiln with the suspension preheaters, and this is the rotary kiln right here. This is where the raw mix material and the mix blending storage. This is the suspension preheater. Then it goes into the kiln, and after cooling, this is the clinker storage. This is just, a photo of a typical cement factory. So what type of fuel we use in the kiln? Any type of hydrocarbon fuel, coal, coke, natural gas, oil can be used. But these are expensive. And again, to reduce cost, we can use many waste products, such as used motor oil, wood, tires, cellulose, and others, wood chips, etc. This will not only reduce costs, but also help reduce the carbon footprint. And you remember, the production of 1 pound of cement or concrete produces 1 pound of CO2. So by using these recycled materials or waste products, we kill 2 birds in 1 stone. We save energy and we reduce the carbon footprint. Okay. So again, using alternative materials is one of our missions as concrete professionals. So let's really, I know we talked a lot about the various processes, so let's summarize the process. After the raw material is selected and proportioned, the raw material is then crushed, ground, and screened. The material must be homogeneous and uniform. The material must be finely and uniformly ground to achieve burning at the lowest possible temperature. So proper preparation of the raw meal will save fuel and also prolong the life of the refractory, which is the heat-resistant ceramic material which line the kiln. And also it will achieve more uniform product. Okay, so basically, the feed-in, the crushed ground material, which is, I said, less than 75 to 90 micron, and screened raw mix into the rotary kiln and heating it to a temperature on the order of 1450 to 1550 Celsius. And again, I'm going to have to re-emphasize, a key factor is the homogeneity of the mix. Okay, the sequence reactions as follows. A temperature of about 100 degrees, this is the drying zone, free water is expelled. In the preheating zone, about 750 degrees, firmly bound water from the clay is lost. In the calcining zone, 750 to 1000 Celsius, calcium carbonate is decomposed In the burning zone, about 1000 to 1450, partial fusion of the mix occurs with the formation of C3S and C2S. In the cooling zone, between from 1450 to 1300, crystallization of the melt occurs with the formation of calcium aluminate and calcium aluminoferrite. After firing the raw materials for the required period, the resultant clinker is cooled. The clinker again is dark gray porous nodules, with the size being between 6 to 50 millimeter in diameter. The resultant clinker is then, I said, cooled using air while on a moving grate. The rate of cooling impact how reactive the cement is. So again, the many tests done on the cement after that, this is one of the quality control processes. After cooling, the cement, the clinker is then ground with about 4 to 5% gypsum to a specified degree of fineness. Usually certain grinding aids are generally polar compounds are added to facilitate grinding, such as maybe ethyl glycol. And again, once it's ground with gypsum, it becomes Portland cement. Before that, it's just clinker. After the addition of gypsum, which is the sulfate source, it is called Portland cement. After that, the product is shipped, in bulk or bagged or, however. This is again a schematic diagram here showing the process from quarry to shipping the cement, and again all the processes we talked about: quarrying, crushing, storing it, grinding the material, doing the quality control on the feed, feeding the material and the suspension tower, going through the kiln. After that, cooling the clinker, storage of the clinker right here. And then, we have the gypsum silos here, and we have the finish mill of grinding. These are the cement silos, and after that, it's ready for use. Okay, so I'm gonna, repeat a couple of things. So the clinker chemistry and what comes out of the kiln, the major phases, as I mentioned in earlier slide: tricalcium silicate, about 50 to 70%, dicalcium silicate, 15 to 30, tricalcium aluminate, and tetracalcium aluminoferrite. Again, I said these are the major phases. As we mentioned, the composition of the clinker and eventually the cement can be varied by varying the proportion and the chemistry of the raw feed. Okay, so there has to be a rigorous quality control process on the cement, making process. Cement manufacturing is very complex and extremely expensive. So almost no room for error, because any mistake is expensive. So a rigorous quality control system must be in place, from selecting the location, which is the quarries and availability of raw materials, to controlling the temperature inside the kiln, as it will affect the chemistry and morphology of the phases, to the cooling rate, which also will impact the reactivity of the cement. So again, it's a very involved process, and quality control is key. This is here, some micrographs basically of how, clinker will look like under a powerful light microscope. These clinker samples have been, cut polished and maybe etched with certain materials, basically etching with certain materials, color different phases with different colors in order to be able to view it under the microscope. This is, part of the quality control process and studying the composition of the cement, and also mostly the morphology, the shape, and the texture of the phases. We might go over this again in some other lecture, but I'm mentioning it here for reference, just so that you know about it. Okay. There is a good source for really seeing how the manufacturing process. There is a virtual tour available on PCA, Portland Cement Association website, and here is the link. You could actually visit it, and it's pretty cool, and really gives you just an exact idea and imagination how the process works. Okay, this is it for the manufacture of Portland cement. Thank you for watching, and I will see you next time. Next lecture, we will discuss the composition of Portland cement. And again, thank you, and I will see you next time.